In this video, I wanted to show you how to use the limit laws to actually solve limits, because that is the point. And in the previous two videos, I talked about number one is there are rules that can allow us to solve limits to avoid having to look at graphs or plug in numbers. And in the second video, I talked a little bit about the structure of how limits can be broken down. And now let's try to use them and put them into action. So let's say we're looking at the first example in our packet, the limit as n approaches 4 of n squared minus 2n plus 6. Again, you could graph it, you could plug in 3.9, see what happens, or even plug in 4 and see what happens. But let's talk about how we would use the limit laws. But first of all, there are a lot of ways you could go about doing this, but how I would choose to do it is, well, I would notice that in this I have a polynomial. I have three terms, sometimes called a trinomial. But what limit law number 3 tells me is that I can break down a limit of multiple terms of multiple functions into individualized limits. So if I'm looking at this example, I could break this into 3 individual limits if I wanted to. That would give me the limit as n approaches 4 of n squared plus the limit as n approaches 4 of, minus, because there's a minus in there, because the subtraction symbol will be consistent between them, minus the limit of 2n, plus the limit as n approaches 4 of 6. And each one of these individually can help me to solve the, basically a lot of these limits are simpler once I break them down into parts. Like, for example, the limit of a constant is a constant. And there is another limit law which should be noted. Limit law number 6. I totally forgot to address this in the last video because I don't know why. But it's sometimes called the coefficient rule, which says that the limit of a coefficient times a function is equal to the coefficient times the limit. Or another way of kind of visualizing this rule is that if I have a number multiplied to a function of x, that number, again, assuming this does not involve x, can be passed through the limit out front and will not affect the actual value of the limit. Or essentially, I can just take whatever the value is of the limit and multiply it by whatever the constant were in front. So putting that into action, looking at the second component, notice how this one is 2 times n. And my point is this 2 can be passed through the limit because that's a constant multiplier which will not affect the limit. And if you're wondering, okay, well, why does that one make sense? I didn't even confront that in the previous video. It's just an elaboration on, it comes from algebra. But if, let's say, we're looking at law number 3, and let's say both of them were f, the same function instead of f plus g. If we had f plus f of x, what that would give us is 2f of x inside our limit. So we would have a constant coefficient, like, say, 2 as the value of c. What we could do is we could break that down into limit of f plus limit of f, and that would give us twice the limit of f, which is what this right-hand side is saying, is that if I have 2 functions on the inside, I can move the 2 outside. The limit will just be twice the value of the individual limit as an extension of, well, actually, law 3 or law 4 could both make sense of why this works. At the end of the day, it's more important that you know how to work with limits as opposed to why. But as you guys know, my videos, I always try to teach you guys why these things make sense. But looking at the first step, well, with n squared, we could use law number 2 to, sometimes I like to call this taking out or extracting the exponent. So this would be equal to the limit as n approaches 4 of n quantity squared. And in the second part, as I was just saying, this 2 we can pass through the limit. That would give us 2 times the limit as n approaches 4 of n. Also, a lot of times when we write a number in front of a limit, it's always implied that that's multiplied to the limit, just like if we have 2x. And then also the last limit, we could just solve this because the limit of a constant is just equal to the value of the constant. And now what we're left with, as you'll notice, is, well, in both of these parentheses that I wrote, I just have the limit as n approaches 4 of just n, and both of those are just n by themselves. And like with this rule, law number 7, which is the limit of x is just a, well, it doesn't have to be x. This works for any variable. X is what we often use most commonly in math just to be consistent, but in this case, we have the limit as n approaches 4 of n. And again, it's a match. It's exactly the same thing. And as n approaches 4, of course, n will approach 4. So essentially, this just is 4. 4 squared minus 2 times 4 plus 6. And, you know, this is the same exact limit, right? I'm allowed to plug in the 4. And what I end up with is, well, 4 squared, 16 minus 8 plus 6, which is, of course, going to be 14 to solve the value of my limit. And you can go ahead and check that with your calculator. You can graph it, whatever. You can always verify a number of ways as you're practicing solving limits this way. And before we wrap up this video, one thing that you probably notice as well, in this original polynomial, that was just n squared minus 2n plus 6. What we ended up with was the exact same thing, but we just plugged in 4. And probably what a lot of you guys are thinking is, well, I can just plug in, you know, if I have the limit as n approaches 4, sorry, this is way too big. Let me undo that. The limit as n approaches 4. I can just plug that 4 right in because that's what I end up with, right? The conclusion that you might draw from this is, well, the limit as n approaches 4 of this function just results in evaluating the polynomial at the values, because limits I can take out the exponents, I can separate them through the addition and subtraction, and what I end up getting is just the limit of n at the end of the day, which is, of course, just equal to the value, the target of the limit. And that conclusion is correct most of the time. However, there's some instances where you can't do that. We'll look at that in the next video. But one important thing to notice is that a lot of times limits do come down to just evaluating the function at the point, which is a matter of just doing a little bit of arithmetic. But there are instances where that does not work, and that is the entire point of limits to begin with. But the thing that I think is really important here is that limit laws can make it easier to break things down and solve them algebraically.